Okay, in today's lecture, we're going to cover the first part of the section 4.5 material on the dimension of a vector space. So in our previous section, 4.4, we had seen that a vector space V, which has a basis B consisting of n vectors, is isomorphic to Rn. So that is, the vector space V acts like Rn, or vectors within that vector space V act like vectors in Rn. And since we're familiar with vectors in Rn and their properties, we can convert vectors in a general vector space to vectors in Rn using a coordinate mapping, and establish properties for that set of vectors in Rn, and the corresponding vectors in our vector space V will have those same properties. For instance, linear dependence or independence. Now, in this section, we're going to show that the number n, that is the number of vectors in our basis for a vector space, is an intrinsic property of the vector space V called the dimension of that space. And the dimension does not depend on the particular choice of basis for our vector space. So if there's more than one basis for a space possible, we'll see that the dimension for that vector space will be unique. Now, our discussion of the dimension throughout this section will give us some additional insight into properties of bases, so we'll see that throughout this section and the remainder of Chapter 4. So to start this section, we're going to state and prove a couple of theorems which will allow us to define the dimension for a vector space. So our first theorem, 4.9 from your textbook, says if a vector space V has a basis B consisting of the vectors b1 through bn, then any set in V which contains more than n vectors must be linearly dependent. So any set of vectors from the vector space V where the number of vectors is larger than the number of vectors in the basis must be a linearly dependent set. So let's take a look at the proof of this theorem. So here we're going to consider a set of vectors, let's say u1 through up. So this is a set of vectors in our vector space V, where the number of vectors, p, in this set is greater than the number of vectors for our basis, n. So let's take a look at the coordinate vectors. Let's say the coordinate vector of u1 relative to the basis b up through the coordinate vector of up relative to the basis b. So these coordinate vectors are vectors in Rn, and these will form a linearly dependent set in Rn, since the number of vectors which is p, we're looking at p coordinate vectors, is larger than the number of entries. For those vectors, which was n. So here, since we had n basis vectors, each of these coordinate vectors is a vector in Rn, but we have p total vectors in Rn, where p is greater than n. So recall from our Chapter 1 material that if we have more vectors than the length of the vectors, that set must be linearly dependent. So linear dependence here means that there exist scalars, let's say C1 up through CP, which are not all 0, such that a linear combination of these coordinate vectors with respect to the basis B is equal to the 0 vector in Rn. So here we're looking at a vector of n entries which are all 0. Now, since the coordinate mapping is linear, as we established in our last section, this linear combination of coordinate vectors for u1 through up on the left-hand side of our equation is the same as the coordinate vector of the linear combination of u1 through up with respect to or relative to that basis B. So this is still equal to the 0 vector in Rn. So that is the vector of n zeros. Now recall the definition of this coordinate vector. So the expression that we have here, the entries of this coordinate vector for the linear combination C1, U1 up through CP, UP, are the weights of the basis vectors from this basis B, such that a linear combination of those basis vectors would give us the indicated linear combination. So using that definition, we have the vector C1, U1 plus C2, U2 up through CP, UP is equal to 0, that is our first coordinate for this coordinate vector, times the first basis vector from B, plus so on up through 0 times B sub n, since all of the weights here were 0. So the sum of these 0 terms gives us the 0 vector in our vector space. Now, since we've already established that these scalars, C1 through CP, are not all 0, that means we have a linear combination of the vectors U1 through UP, where the weights are not all 0, which is equal to the 0 vector. So that is the definition of a set of linearly dependent vectors. If there's a linear combination of these vectors with not all 0 weights such that we have the 0 vector. So we can say these vectors, or the set of vectors U1 through UP, is linearly dependent. So that's what we wanted to establish, is any set of vectors where there are more vectors than the number of vectors in a basis for that space must be a linearly dependent set. All right. So thinking about what this theorem says in a bit more detail, this theorem implies that if we have a vector space V with a basis B consisting of n vectors, then each linearly independent set in V has at most n vectors, because any set which contains more than n vectors would have to be linearly dependent. So we can say every linearly independent set from that space has at most n vectors. All right. So let's look at another result, which will then allow us to define the dimension of a vector space. So this next theorem, 4.10, says if we have a vector space V, which has a basis of n vectors, then every basis of V must consist of exactly n vectors. So in this theorem, we're trying to show that if we find a vector or a basis for a vector space, then every basis for that vector space must consist of the same number of vectors, which we're calling n. So let's see if we can establish this using theorem 4.9. So let's suppose that B1 is a basis of n vectors and let's take B2 to be any other basis of this vector space V. Now, since B1 is a basis and B2 is linearly independent, that means that B2 has at most n vectors by the theorem which we just established, theorem 4.9. So recall theorem 4.9 implied that any linearly independent set within our vector space consists of at most n vectors. Now here, we're using the fact that B2 is a basis of our vector space. So by definition of a basis, the vectors within that basis must be linearly independent. So since B2 is a set of linearly independent vectors, theorem 4.9 guarantees us that B2 has at most n vectors. So we've shown that there are at most n vectors. Now we need to still establish that there are exactly n vectors in this second basis B2. So let's see that there are exactly n. So we can say since B2 is a basis and B1 is linearly independent, because B1 is a basis, that by definition it has to be linearly independent. That means that B2 has at least n vectors by theorem 4.9. So since B2 is a basis and B1 is linearly independent, that means that B2 cannot contain fewer than n vectors because then B1 would not be linearly independent according to theorem 4.9. So we've shown that B2 has at least n vectors and it has at most n vectors. Therefore, it consists of exactly n vectors. So we can say our basis B2 consists of exactly n vectors, which is what we wanted to establish. Okay. So this will then allow us to state our definition of dimension that we're going to talk about throughout this section. So if we have a non-zero vector space V, which is spanned by some finite set S, then a subset of S is guaranteed to be a basis for V by the spanning set theorem. So in this case, theorem 4.10 ensures that the following definition will make sense. So here, if we have some finite subset spanning our vector space, we know that every basis will consist of exactly as many vectors as that basis. So we can say if V is spanned by a finite set, then V is said to be finite dimensional, and the dimension of V, written as dim V, or dimension of V, is the number of vectors in a basis for V. And by theorem 4.10, we've seen that the number of vectors in any given basis has to be the same as a given basis in vectors. Now, by definition, we will use the convention that the dimension of the zero vector space is defined to be 0. So that is the space consisting of only the 0 vector will have dimension 0. And if V is not spanned by a finite set, then we say V is infinite dimensional. All right, so now that we have defined the dimension of a vector space, let's look at some examples working with the dimension, or identifying the dimension of some familiar vector spaces. So in this problem, we're asked to determine whether each vector space is finite dimensional or infinite dimensional. And if so, that is, if it is finite dimensional, find its dimension. So in part A, we have the vector space Rn. So let's think about a basis for Rn. So for Rn, the set of n-dimensional vectors, the standard basis is the set, let me give it a name. I think we've been calling it E, which would be the set of vectors E1 up through En, where E1 through En are the columns of the n-dimensional identity matrix. So here we have a basis which consists of a set of n vectors. And by theorem 4.10, every basis for Rn consists of exactly n vectors. So the dimension is the number of vectors in a given basis. Since we see there's a finite number of vectors, we can say Rn is finite dimensional. And the dimension of Rn is n, the number of vectors in our basis. Now in part B, we have R infinity. That is the set of all infinite sequences with real entries. So recall that a typical vector in Rn would have the form x1, x2, and so on. So it's a vector of infinite length. So here a basis, really the standard basis for Rn would be a basis, let's call it B, consisting of vectors of the form E1, E2, and so on. But we have an infinite number of these basis vectors. So E1, E2, and so on are the columns of an infinite dimensional identity matrix. So for instance, E1 has a first entry of 1 and zeros everywhere else. E2 would be 0, 1 with zeros everywhere else. E3 is 0, 0, 1 with the remaining entries being 0, and so on. So here, since any basis would have to be infinite, we can say that R infinity is infinite dimensional. All right. Now in part C, we're looking at the vector space of 2 by 2 matrices with real entries. So recall from, I believe it was section 4.1, we saw that the standard basis consists of the 2 by 2 matrices 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So any 2 by 2 matrix with real entries can be expressed as a linear combination of these 4 matrices. So this space is finite dimensional, and its dimension is equal to 4, since we had 4 vectors or matrices as the basis vectors. Now, we could generalize this. So if we were to consider, let's say, the space more generally of m by n matrices with real entries, the dimension of this space would be equal to m times n, the total number of entries in a given matrix. And we could take basis vectors that are similar to the 4 that we saw here. All right. So in part D, we have the vector space P2, that is polynomials of degree 2 or less. So recall that the standard basis for this set or for this space is the set of vectors 1, t, and t squared. So since this basis contains 3 vectors, theorem 4.10 guarantees that every basis will contain 3 vectors. And so the number of basis vectors is what we call the dimension of this space, and it would be equal to 3. So a little more generally, let's say in part E we have the vector space of polynomials of degree at most n. Well, the standard basis for this space would be the set 1, t, t squared, and so on, up through t to the nth power. So in total, let's count the number of vectors that we have for this basis. So we have t to the first, t squared up through t to the n, so that's n vectors, but then we also have this constant 1. So we've got a total of n plus 1 vectors within our basis, so that number is the dimension of this vector space. So in our last one, part F, we have sort of this boldface P, which represents the set of all polynomials, or the space of all polynomials, which has a basis given by 1, t to the first, t squared, and so on, up through t to the nth, and so on. Since there is no limit on the degree of the polynomial here, we would have an infinite basis, or a basis consisting of infinitely many vectors. So this space of all polynomials is infinite dimensional. All right. So here, getting familiar with the idea of the dimension of a vector space. It is the number of vectors in any basis for that vector space. So let's look at some other examples working with subspaces, which are themselves vector spaces, and see if we can identify the dimension of a given subspace. So in our first example, we are asked to find a basis and then state the dimension of the subspace H of vectors in R3, consisting of, or which are of the form 4s, negative 3s, and negative s, where s can be any real number. So we see here that for any vector, let's call it x in H, x has this form, 4s, negative 3s, and negative s, which can be written as s times 4, negative 3, negative 1. So we can think of H as being the span of this vector, which we've shown here. Let me give this vector a name. Let me maybe call it V. So here H is the span of this vector V, and any set consisting of a single vector must be linearly independent as long as that vector, in this case V, is something other than the zero vector. So we have H is the spanning set of this linearly independent vector V, which means that that vector forms a basis. So here, since V is not the zero vector, V is linearly independent. So we can say a basis for this space H is the set, maybe call it B for basis, which would be the set consisting of the single vector V. So since the basis consists of a single vector, theorem 4.10 says that every basis would consist of a single vector, and so the dimension of this subspace H is equal to 1. All right. So we can think of this subspace H in R3 as being a set consisting of a line pointing in the direction of this vector V passing through the origin. So a one-dimensional subspace we would have for a line in 3 dimensions in space. So let's look at another example. In this next one, we have the same sort of problem where we are asked to find a basis and state the dimension of the subspace H, whose vectors have this indicated form. So, as with our last example, we can say for any vector x in this subspace H, x has the form shown here, and we can decompose this into a linear combination of vectors with weights a and b. So we could take this as a times 1, 2, 3, 0, plus b times 1, 0, negative 1, negative 1. So these two vectors, let's give names. Let's call them v1 and v2. And we see that any vector in H can be written as a linear combination of those two vectors. So H can be considered as the spanning set of the vectors v1 and v2. And we can see by inspection here that v1 and v2 are clearly not multiples of each other. So v1 and v2 are linearly independent. Which means that the set B, consisting of the vectors v1 and v2, is a basis for H, and the dimension of this subspace H is equal to 2, since there were 2 vectors in our basis, and theorem 4.10 says there's 2 vectors in any basis for this space. All right. So let's look at some other ones. In this next example, exact same sort of problem. We're asked to find a basis and state the dimension of the subspace H, which is a subset of R4, where the 4 entries of our vector are defined in terms of A, B, and C, which are entries in R. So as with our previous examples, we can see that for any vector x in H, we can express x as a linear combination of vectors with weights A, B, and C. So for instance, we would have A times 3, 6, -9, -3, plus B times 6, -2, 5, 1, plus C times -1, -2, 3, 1. So these 3 vectors, let's call V1, V2, and V3. So the entries of V1, V2, and V3 are the coefficients of A, B, and C in the components of this general vector x, taken from our subspace H. So we can say here that H is equal to the span of this set of vectors V1, V2, and V3. However, in this example, notice that the vectors V1 and V3 are scalar multiples of each other. In fact, V1 is equal to -3 times V3. You can check that by examining the components. If I take the vector V3 and I multiply by -3, I would have a +3 for the first component, +6 for the second component, -9 for the third component, and our -3 for the last component. So we see that V1 and V3 are linearly dependent. So the spanning set theorem says if one vector can be expressed as a linear combination of the others, then our spanning set can be reduced by that one vector. So we have the span of V2 and V3 would be the same space, since any vector V1, or a scalar multiple of V1, can be written in terms of V3. Now comparing the vectors V2 and V3, we can see pretty quickly that they are linearly independent, because if we look at the second components, well, the second components are identical, so if these two were scalar multiples of one another, that scalar would have to be 1, but we see that the first entries are not that same scalar multiple of one another. So here H is the span of the vectors V2 and V3, and V2 and V3 are linearly independent. So the set B, consisting of V2 and V3, is a basis for this subspace H, and since there are 2 vectors in this basis, the dimension of our vector space, which was H, is equal to 2. All right. So in our next example, we've got the same sort of problem. We're asked for a basis and the dimension of the subspace H, which consists of vectors in R4, A, B, C, D, where these coefficients, A, B, and C, are related by the following equation, which can be rewritten as A is equal to 3B minus C. All right. So here, for any vector x within this subspace H, we can write x in the form A, B, C, D. However, we're given in the definition of this space, A, the first component, is equal to 3B minus C. And then the other components, B, C, and D, are the same. So we can decompose this as a linear combination of vectors with weights B, C, and D. In particular, B times the vector 3, 1, 0, 0, plus C times negative 1, 0, 1, 0, plus D times 0, 0, 0, 1. So these three vectors, let's give a name to, let's call them V1, V2, and V3. And by inspection, we can see that those three vectors are linearly independent. No one of these vectors is a linear combination of the other two. Therefore, they must be linearly independent. So we can think of H as being the span of the set of vectors V1, V2, and V3. And these vectors, V1, V2, and V3, are linearly independent. Another way to check linear independence here, you could take a matrix which has this V1, V2, V3 as its columns, row reduce it, and show that the only solution to the homogeneous linear system with that coefficient matrix would be the trivial solution. So here we've found that these vectors are linearly independent. Therefore, the set B, consisting of these vectors, V1, V2, and V3, is a basis for the subspace H, and our dimension for the subspace H is 3, the number of vectors in our basis. So in this first part of our section, we've established a couple of results for vector spaces, namely a vector space that has a basis in will have any other basis as containing the same number of vectors in. That is, any basis for a given vector space must consist of the same number of vectors in, which is called the dimension of our vector space. And we've seen some examples for frequently used vector spaces or subspaces of a given form, how to determine that dimension.